Hi everyone, welcome back to my series on creating a chain of talk LLM. In the first three videos of this series, we have trained 1 2.5 to be equipped with mathematical and medical reasoning capabilities. Further, we have seen how to do inference with prompt routing. This is necessary in inferencing with chain of talk model which has multiple specialized knowledge. In this video, we'll go through the step to do inference with Retrieval-Augmented Generation. In RAG, the model integrates external knowledge before generating the answers. We will cover two RAG techniques which I have learned. So the first one is RAG with local document. In this case, we will retrieve and incorporate information from the local documents. The second one is retrieval of information from web data. In this case, we will crawl the web for relevant information and fetch them into the model as context. Now let me open the notebook. So here I'm using Lightning AI for the GPU. For this video, I created a folder which I call RAG local. On this folder, there will be two files, data and inference. Both of these files are available on my GitHub repo. So the first step is to prepare the data. The data that I'm using here is a PDF file, a medical PDF file. So let me try to load this. So this is the file. It has about 100 pages. It is just some documentation about medicine that I find on the internet. Now let's get back to the notebook. First, you will need to install necessary libraries that I list here. We will need to import OS. Tick token here is for counting the number of tokens. We will use recursive character text splitter from LangChain to split documents into chunks. We'll use hacking face embedding to embed an embedding model. We'll use FAISS, which is a package from Meta AI to search for similarity. And we'll use PyPDF loader from LangChain to load PDF document. The first function here is simply a function to count the number of tokens in the text using tick token. Okay, let me just extend this. The second function is split documents. So this function has argument as document path. We will split the PDF document in this case into smaller chunks, and to do so we use recursive character text splitter. We in the splitting we ensure that chunks are appropriately sized for embedding and retrieval, and we also count the total chunks together with the total tokens. We return a list of split document objects. So first, we will load the document using PyPDF loader. So we initiate a loader with the given document path, and page here load all the page of the documents. We initialize a splitter with tick token encoder. So this is our text splitter. We use recursive character text splitter from tick token encoder. So the chunk size in this case is set to 2000 and the overlap size is 100. So that means each of the chunks has 2000 tokens, and for any two chunks they are allowed to have 100 tokens in common. In order to split the whole documents into chunks, we use the method text splitter dot split documents. So here it gives us a list of document objects. We print out how many of them are there, and then we count the total number of tokens in all the split documents simply to see how many tokens in total we have. And we return the split documents. So this is a list of document objects. Next, we are going to create a vector store in order to store all the split documents. Note that each of the split document here is just purely text document. You can view them as text document. And to make them work, we need to convert each of the text document into a vector. And in this case, we need to use an embedding model to convert them into vectors in some vector space. So in this case, we will use FAISS. This will give us a vector store containing all the embedded documents. So this gives us a collection of vectors, each correspond to one split document. So we start with initializing the text embedding model. The model that I use in this case is the BGE base model. And here are the standard keyword arguments. We create the vector store from the documents using FAISS. So we define the path to save the all the vectors in the vector store. So in this case, I named the path to be local vector store. And if I come here, you can see I already run this file. So this inside this file give me the vectors that I need to store. So we define the path, which is usually named persist path, and we initialize the vector store by the method FAISS.FromDocuments. We put in the split documents, which are the documents that we split out, which will be the output here. And we define embedding to be the embedding model from Hugging Face. And once we have run this, it means the vector store is created successfully. We save it into the local path. And here is the main functions. So first, we will split documents from the local PDF file, and then we create a vector store. Why we need to create this vector store? Because we are going to code it in the inference script later. So once we have this, whenever we want to code it using our local computer, we can simply refer to it. And here is an example usage. The example query here is what are symptoms of flu. I will search in this vector store for the document that is most similar to this query. Note that FAISS use L2 distance to measure the similarities between vectors. So the smaller the distance is, the more similar the vector will be. In this case, lower is better. Here I set the threshold to be 0.5. So I only select the documents that are at distance at most 0.5. I only consider those to be similar. So here you can change this number and observe the behavior. Document with scores will return a list of document and score. So here I use similarity search with score, and I input the query with the value of k. K equal to 2 means it will return the two most similar documents from the list of split documents. And now we are going to get relevant documents. So here, for these two documents, they might not be guaranteed that they are similar enough to the questions. So I only fill out those documents that are at distance at most 0.5 from the questions. So we will print out all the distance from these two documents to the questions. So if the score is less than the maximum distance, we will accept this document and append it to the list of relevant documents. If not, we simply print out that the document has large score or it is too far, and we don't select those documents. And at the end, we print out the number of relevant documents that we select. So, okay, interesting. I already have GPU here. Let me start this. First, I need to install all these dependency. And then also install unsloss. Okay. Now let's move to the correct folder. So we are working on RAG local inference. Let's move here. So in the beginning, we shouldn't have this local vector store. Let me maybe just delete this, and I will run this file again. So we will do python data.py. So here you can see it print out that we have 100 chunks from the documents, and total number of tokens is 66,000 tokens. Next, we are loading the embedding model, and we will create a vector store. All right, so here is the result for the question. The query here is, what are symptoms of flu? So it looks like this document do not contain the information about flu. Let me check what they are, what type of information they contain. So this is just introduction to clinical medicine. Okay, let me just input these questions and try again, and hopefully this time it gives us some answers. Okay. Well, looking back to the previous case, we can see that we have two distance, about 0.9, and these are not accepted because we set the max distance to 0.5. For those documents that are accepted, here we also print out the documents. So to print out the documents, in fact, each of the document here is a document object. If you want to print out the document, you need to use the method .pick_content to view all the content in the document. D.metadata source here gives us the metadata for the document. Document is still too far. Perhaps I set the score too low. Let me just change this to 0.6. So in this case, it should have one document, because just now we have seen that the top two have distance 0.5, 0.6. So in this case, it should give us one document. Yeah, we have no relevant document here because the scores are not within the max distance. Okay, now it is done and it looks good here. So here we have two document distance. One is 0.56, which is selected. The other one has distance too far and not really selected. And here we retrieve the document. Yeah, so here we can see this exact sentence, which is the one that I copy from the document. So it looks good. So that is data preparations. So now note that we have this local vector store on our computer. We can call it anytime. Next, let's move to the inference script. Well, in inference, first we need to import the necessary libraries. We need unsloss, torch, the token we will use unslots to load the model and to do the inference. I guess a few. This one is not needed here. It's only used for the web crawl. Okay, so now let's go to the inference script. Well, all these unnecessary. I must have copied them from the other file, and all these are unnecessary. We will start with the loading of the model and the tokenizers. So our fine-tuned model is saved in this adapter path, GRPO LoRa. So this is the path for the fine-tuned model. So in this path, we have saved the model that was first trained with reinforcement learning using GRPO, and then fine-tuned on the medical chain of talk dataset. To load the model, in this case, so note that we are in this folder, and our adapter path is one level above. So first we need to go up one directory from the current working directory before we can get the path to the model, the absolute path to the model. So to do so, we use os.path.directory name of the current directory, and we join it with this name of the adapter path. So here is a usual routing for a LoRa model. We load the base model and the tokenizers from fast language model. In this case, I set max sequence length, which is the context length, to 4200. Why is that the case? Because recall that when we split out our documents, well, if you go back here, when we use the text splitter, the chunk size is 2000 tokens, and when we search for document similarity, we set k equal to 2 as here. So we search to up to 2 documents that have similar content to the questions. So that means we have total 4000 tokens. So our max sequence length here should be at least 4000. And here I set 4002, so that 200 tokens will be used for question. We set load in for bit equal to save the memory, and we set device map to auto. We apply the LoRa weights to the base model. So here you need to copy the exact configuration that you use when you fine-tune the model into this case. Otherwise, when you load the adapter, there could be an error. So we get PEF model, and finally we load the LoRa adapter from here. We put the model in evaluation mode because we will only do evaluation from now on. We also load the tokenizers, and we return the model with the tokenizers. Well, the next step, I have a code that is used basically to clean up the memory space. So when I run this inference script, it is going to load the model and do inference based on my input questions. So I want that when I stop running the script, the space, the memory will be clear. So when I finish running the script, I will delete the model and I will empty the cache. And here are a few global variable names, which are basically the system prompt that you already see in the video about prompt routing. Note that our models are equipped with specialized knowledge in mathematics and in medical. So when a question is received, it will first need to determine what type of question that is and whether it needs to use its specialized knowledge. And in the case it needs to use a specialized knowledge, we will tell the model about its role. And this is where all the system prompt come in. So for math system prompt, we tell the model that you are an expert in solving math problems. You first think through the reasoning process step by step in your mind and then provide the user with the answers. For a medical system prompt, we tell the model that it is a medical expert. And for other prompt template, we tell the model that it is great at answering all the questions not from the teams math and medical. And here I use a list to store all these prompt templates. For selecting the prompt based on input questions, I'm going to use the method by the LLM itself. Why that is the case, I have experimented the other method, which is by an embedding model. However, I find that using the LLM itself is more accurate. The reason I believe is because the embedding model will only compute the distance between the question and the prompt, and it doesn't really understand the wordy meaning of the question and the prompt. Some question might, let's say, might not have common words with the prompt. However, they might be of that topic. For example, I might ask a question, what is 1 plus 1? When we use an embedding model and embed that sentence into some vector space, that sentence might have very little common words with the system prompt telling the model that it is a math expert, and hence it might not choose this system prompt as the knowledge that the system need to assume. On the other hand, if I ask an LLM that you are a text classifier given an input text, respond with exactly one word, math, medical, or others, output only that word, no extra text, and give it a few examples. And if I ask it what is 1 plus 1, it should be able to categorize that question is in the category math. So the most important thing in classifying the prompt type by LLM, in my opinion, I believe, is the system message. So we set this is the message using a few short prompts telling the model what to do, that is to classify, and also give it example on what type of output it should give. So this is the system message, and for user message, we ask the model to classify based on the question. We also prompt with the word category, so the model know that it need to follow up with this word. The list of message here will include the system message and the user message. There is no assistant message here, and because there is no assistant message, when we tokenize this list of message, we will set at generation prompt equal to, so that the model say no, it should start generating after the user message. And we tokenize the prompt here by returning the tensor type as PyTorch. For generating the output tokens, note that we want to classify whether the input text is in one of the categories math, medical, or others. So for the output, we only need the tokens that are enough to cover these three words. So I only set the number of output tokens to 2. So we set max new token equal to, and in this case we don't do we don't even set a temperature parameters. We want to choose the logits which has the highest value in the list of output tokens. And for the response, we only return the part that is generated by the model. So this is just the usual routine. So now comes to the main function, which is the inference functions. So for this function, we have the input arguments as model, tokenizer, and the input questions. So first we initiate a dictionary to convert the question type to temperature and prompt template. Prompt type to temperature here is basically a dictionary with keywords mass, medical, and others. For mass, we will set temperature in the inference to 0.1. Note that lower temperature means more deterministic. So for question about mass, we want the model to answer in a deterministic way and don't try to be too creative. So we set a low temperatures. For medical, because the model was trained on a medical dataset, it has some knowledge. So we also set a low temperature. However, it is not as too low as mass. So we set it to 0.4. For others, we set it to the default temperature, which is usually 0.7. For the system prompt template, for mass, we use mass prompt template. For medical, we use medical prompt template. And for others, we use other system prompt template. There are a few steps in the inference functions. Note that we are going to inference with retrieval-augmented generations. So the first step is to get the context for the question. If the question, in fact, is related to the file that we just work on, that is medical file here. So for getting the context, we will first get the system prompt and temperature from the question type. Okay, I would say getting context start from after this step. And note that earlier in the file data.py here, we already created a vector store for the documents. So here is the path to the vector store, and now we simply load this vector store, right? Using the method load local. In this method, we need to specify the path, specify the embedding model that we use, and we set allow dangerous deserialization to true. This is safe to do so because we create the local vector store. And then, given the question, we search for the two documents that are most similar to the documents we set. Here we also filter out the documents among these two. We only select the document that is at maximum distance 0.7. In this case, I set 0.7 to the questions. So we set max distance, and we look through these two documents and select the one with a distance that is at most 0.7. After we have selected the relevant documents, we will combine them into one single context that will be provided to the LLM. If there is no relevant document, which means both of these two documents have distance bigger than 0.7, in this case our context will be none. On the other hand, if we have some relevant document, and in the case we have two, right, we will join them using two n-line characters, and we print out how many relevant documents we use for context. And now we have the context. We will set the message and then send the message into the model to do inference. For the message, the user message will come from the following template. So here I set a template for the user message. So I say that use the following piece of context to answer the question at the end. If the context is none or empty, simply answer the question based on your knowledge. If you don't know the answer, just say that you don't know. Don't make up the answers. Show your reasoning in thinking tag and return the final answer in answer tags. Stop generating after the answer tags. And then we provide the context and also the questions. So the first three sentences here is to tell the model that you are given a context and the question, try to answer. The next three sentences is to tell the model that it should answer in a way where it first reason about the questions and then provide the final answers. All right, let's see how it works out. Now we set user prompt by formatting this template with the real context and questions. This will be the user prompt, and we form the list of message with system prompt, user prompt. In this case, we will prompt the model to start with the sentence, "Let me solve this step by step," and we even prepare a think token to encourage the model to respond in the correct format, right, in thinking tag, and return the answer in the answer tag. And now we simply we simply feed this message into the model. And here we in generating the response, I do some error handling with a try except block. So we will try to generate response. If we encounter some error, we print out the error and we return the error. So here we form an input by apply the chat template to this list of message, and then we tokenize it. We put this into the model for generations. I set max new token to 1024. Temperature equal to the temperature that we found above. Right? So before this, we already found temperatures based on the question type. Yeah, and we set text. We set the streamer to be a text streamer so that the answer will be displayed in a live fashion. So here is some return. We only return the part that is generated by the model, which means we exclude all these message. All right, so now in the main functions, we use some child finally block to clean up the space when we stop running the code. First, we load the model, and then we will get the input from the user in the command line interface. So we ask the user type the question or type exit to quit. While true, we will keep getting the input from the question from the users. So question here is input from the users. If we have no input, just continue. If the input is exit, we will exit. We will break out of the loop. Otherwise, we will do inference. Right? When we have some error, we simply print out the error. And if we exit the loop, we will clean up the memory. So now let's run this. Let me see. This is inference.py. So it will take some time to load the model, especially with in this case we have two models, the embedding model and also the fine-tune model, but this is quite fast. So let's go here and see if we can add something inside. Let me just draw down. Let's see if something I can understand. I cannot understand most of the things here. Okay, let's just select some things. Okay, what is some pregnancy complication associated with. That looks good. So first, yeah, I should have let it finish the answer before going back. So first, the question start from here, right? So first we see that there are two relevant documents for these questions, and we are going to use these two documents for the context. and here is the system message, and here is the context. We get two contexts, and here is the questions, and assistant start from here. Let me solve this step by step, and think this is the reasoning part, and this is the answers. That's good. Let's try one math questions. Let me go to the data that we train the model on, but we are going to use the data that some questions that the model never see. So we have trained only 1/10 of the data, because there are over 8,000 questions, and we only train about 800. It's safe to pick the question at the end here. Any questions? This is a bit long. I don't know whether it's okay. Let's say this one. So remember that the answer is 49. Let's go back here and ask the question. Ask the model about these questions. Okay, it gets the correct answers, and if you look at the printout here, so you can see it start from here, right? This is the questions that we okay, sorry, this is what we key in, we put in the questions, and all these documents are too far from the question, so we are going to respond without any context. And so here the systems, the model correctly identify that this is a math problem, so it should use its knowledge about math to answer the question, and the answer is correct. Let us the question something that is neither medical nor math. What is the use of LLMs? Yeah, immediately you can see this already. It already identified the question as none of the team math or medical. So all the documents are too far source, and it identify this question is not from the team math or medical. So here it put in its reasoning, and then it give the final answers. This is also the end for this video. I don't want to keep the video too long, so I will separate the part about inference with RAG into two videos. And in this video, we have gone through the step in inference with Retrieval-Augmented Generation using a local document. In the next video, we will see how to do inference where we need to gather information from some website or a list of website for relevant informations. Thank you, and see you next time.